Welcome to the Southeast Pennsylvania section of the AAPT Spring Demo Day. We do this every year at a different location, in theory. This is our second year in a row here. In the fall, we do a more robust, slightly more formal conference, which is a Friday evening and a Saturday, where there's invited speakers. I'm so gratified to see such a great turnout for this one. A lot of new faces, which makes me happy. My message to those of us who come often is don't be too weird, just weird enough to be cute. Keep the mystery. We have a full slate of presentations. Make sure your dues are paid to Mark. $10 a year, very reasonable if you ask me, for these delicious bagels and coffee. What do I want to say? Did I even say my name? Ryan Batkie. I work at UPenn now. I've been coming to these, this is my, whatever April 2008 to now is. That's how long I've been doing this. Currently serving as president of the section. If you're new here, I encourage you to keep coming. Having a culture of specifically physics teachers, I think, has been monumentally important to my own teaching. I credit a lot of my success to what happens in this room and rooms like it. What else do I need to say? I think I'll just do a little soapbox thing for a minute. Demos are wonderful. They build mystery, they're enticing, they pique interest, they pique curiosity, all things we want happening. My note of caution with them is always resist the urge to over-explain. Like you're gonna show something so cool, and that interesting investigation should sprawl out over the next several days, if not a couple weeks, at least. So pick demos that are rich enough that can sustain that interest for several class periods. And don't be afraid to say, that's a really good question.
Hi, I'm Bob Schwartz. I am now a tutor. That's my physics teaching job. I retired a few years ago, taught at Harrington High School, had some really great students at Harrington High School. Some who went into teaching here, and Alissa. So,
2 years in a row.
Wow. So, one of the things I just wanted to make mention on the side, I've been going to these maybe as long as anybody here except Barry and Bill. And I'd say somewhere around 1982 or so. And things that are available now for us as teachers, there's so many things. And one of the upside downsides is all that's available on the internet, because the upside is there's so much to use. The downside is we usually, I mean, this is a great attendance today, and it's hard to get attendance from people who don't, they think need it, because they can get, you know, all the resources they want on the internet. However, it is, this is great, you know, just to be able to meet with other physics teachers, and that's why, you know, for as long as I can remember, always been a proponent of being with a group live, three-dimensionally. So I'm hoping that you guys will talk to other people that you know and try to spread the word. Commercial over. Okay, so
Sorry, got enough tabs.
yeah, I know. I do. People comment. it's like my wallet. I put everything. I have a George Costanza wallet. So it's, I don't know. Anyhow, so I'll just leave that spinning around. I have one of these. Now my talk was to be on Dichroic, which was, I misspelled it in the heading, though it's, really Dichroic cubes. And I found one a few years ago. This is not one of those Dichroic cubes. It's a, they call it a CMY for cyan, magenta, and yellow, the colors you have when you print, what you use in a color printer. And these are so-called subtractive models, so when you combine any two, you get one of the primary colors, like the blue, or the cyan and the magenta, I think if you blue, and it's really interesting. And it was cheap, too, at least for me. I bought it a year or two ago. And I'll pass it around. I cleaned it a little before. So if you look at it, you'll see a blue on one side and a blue on the other, but it's more subtle. I don't know that it was meant to be subtle. When you look at it from one side, let's say the blue toward an adjacent side, because of the symmetry of two yellows, two magentas, two cyans, you'd figure if I rotate it 180 degrees and look through, I'll get the same effect because of that symmetry. But you don't get quite the same effect. I think I know why, but I'll pass it around and just, and what's cool is you get to mix the colors, so it's just a cool looking object. Meanwhile, the thing I did bring, which buying it, they call it a trichroic prism, but.
Are these glass or are they acrylic?
Yes.
Are they acrylic or?
Well, okay, well, they glass. They're probably acrylic, it doesn't say. I just.
Drop it on the floor.
Yeah, thank you. Yeah. It does chip. I'm pretty sure that it is acrylic. That's my guess. So this, which is more expensive, is the so-called, they put here, trichroic prism. And if you look at it, sometimes they call it an X prism because when you look down on from so-called top, the sanded side, you see an X pattern in it. And so, let's see which one they're, oh, that's blue, that's white. So what's cool about it, I think, is if I'm going to send white light through this one, and then adjust, by the way, I forgot, I don't strip for just anybody.
This is for the OnlyFans.
This is now.
Here's your account.
This is the one that you should put on YouTube. Anyhow, it's the closest shirt I have to this, even though this isn't really dealing with refraction, it's directly. So I'm sending a white light through this side, and can you see? It comes out blue there. On this side, comes out, actually, I'm going to move back a little bit, comes out red-ish. And on this side, kind of greenish. If you look directly in without the lights themselves, you'll see it. Yeah, that's a green light. And it's not refraction. Does anybody know about the cube, what it is, or what it's based on?
Diffraction, right?
Hmm?
Must be diffraction if it's not refraction.
well, I mean, it's refraction, except at the point where the regions that matter. The regions that matter is there call it on this picture, a blue reflector, a red reflector, and a no reflector in the sense of green.
It's thin film interference.
Thin film interference, right. And there are two, the thicknesses, for this one to have in reflection a constructive interference for somewhere in the blue portion of the spectrum. For this one, oops, going this way, somewhere in the red part of the spectrum, and this that gets in the middle of the spectrum sort of passes through both, and so you're kind of left with the green part of the spectrum. Now, so where's red? Red's on this side. So the like paths are sort of reversible. So I put a red here where it was coming out before, and you see a strong red there. A not, it's hard for you to see it because it's going right into your eyes, but if I take it away, you should be able to notice a fair bit of red there. And this one, whoops, this one, blue, and here the blue is coming out, of course I'll move the red, there the blue is coming out of this end, not so much, some across the way, but very strong in this direction. And then I have a green one, but no, I don't. I have a,
It's under the track.
It's under the track.
I'm playing with my 10 minutes. And then I take the green one here, and now, of course, this is impervious. The light is diverging. It's also, some I think actually gets underneath, but let me use this. If I go back far enough and then go in to where it's close to the cube, you can see the canyon, the whitish part in the middle. So it recombines the two-way nature of light. I was curious where the heck these things were used besides, oh, anybody know where they're used?
Projectors?
Projectors, yeah. Like possibly this, somewhere in there, because they have individual colored screens, primaries, and then they split them up or rejoin them with something like this cube. Any questions?
Just a point of comment
Or
on
point.
the color cube that's going around.
Mhm.
One other really interesting thing with those is if you have it set up near a window and like it gets direct sunlight, you'll get interesting refractions off of it from internal refractions. So you get different colored like glows in different parts of the room
Yeah.
Based upon those. It's really cool.
Okay. Thank
Well,
you.
they don't notice it. I'm the only one noticing that.
Take it away.
Okay, hi everyone, I'm Alissa Sperling. I work here at SCH. You are in my classroom right now, so if you have questions about anything you see in here, it's either mine or left by the hoarder that had this room before me. So I've been in this room for 11 years, but still, it remains. So I'm going to show you this is the category of demos of so you're running to Walmart and you have $5. You're probably not going to get reimbursed. This is that type of demo. So I'm doing 5 demos for $5. That's actually a $25 total, not a $5 total. Just so that we're clear. It had kind of like a Subway theme, so I wanted to keep the 5 for 5. Okay, they're totally random. I teach physics first in 9th grade, and I teach AP Physics C, so some of these, I'll tell you who they're better for. You could technically use them in either place. So first, this is chocolate. I grabbed it from the fridge. Oh, and also, these are not the world's most groundbreaking demos. You will probably have seen a few. My hope is that none of you have seen all 5. This is chocolate. I melted a dark chocolate Hershey bar last night and I cooled it in the fridge on diffraction grating. If you shine your cell phone on the, see, this is the confused look I want. I want you to be like, I haven't seen this. The internet's an amazing place. So you're gonna need to take out your cell phone flashlight, and when I flip this over, the problem is by the time it gets passed around, it's gonna get a little melty. It will act as a diffraction grating. So I'm going to pass this around. Oh, that's it. Amazing chocolate rainbows. Dark chocolate works better than milk. I haven't yet tried it with the cookies and cream bar in my desk, but I assume it would work badly. So shine your phone flashlight. You can get the pattern from the diffraction film on the chocolate. So, okay. So just move the light around. So if you're talking about diffraction gratings and you want to make it more interesting and delicious, that is food safe. I did wash this. So if anyone wants to eat it, they can.
You get that in the cooking store.
What?
Diffraction grating. How do you get that large?
So this came in my classroom. I since have ordered, it's up in that cabinet. I ordered a giant one. Sorry, I'm gonna be all over the camera. I ordered some off of Amazon up here. And I can give you guys some because I haven't gotten it to work yet, but I think I used the backside. So I have a bunch in here that I ordered. It was like $10, so it doesn't fit in the 5 for $5. You could use the like little diffraction grating and just do smaller pieces of chocolate. So that's like our Hershey bar, and I just melted it in a cup in the robotics microwave and like poured it on. But you could just do smaller dots. So wherever that's passing around, use your cell phone camera and you can see that.
Daughter?
What?
Did you show your daughter that?
No, she'll eat it.
That's the reward for watching.
Okay, so that's demo, $5 demo number 1. Diffraction grating's quite cheap. I'm happy to give you some of the stuff that didn't work for me. Here's demo number 2. This is stolen from my favorite high school physics teacher. So you guys have probably seen this, but I have a fun little take on it while we're in light. So you may know that vegetable oil has the same index of refraction of Pyrex. What makes this $5 is that you steal the Pyrex from the chemistry lab. So that's the key. You just buy the oil in the Tupperware. What I like to do is tell the students, like, I have this Pyrex stir, and they're always like, what's Pyrex? You have to pull up a picture of a measuring cup. And the 9th graders are like, oh, I have that in my kitchen. And you're like, yeah. And you let them touch it. And then I tell them I'm a powerful warlock, capable of dark and terrible things, which is like a general theme for the year. Put this in. And did any of you want to take a look? Has anyone not seen this demo? Great. Someone who hasn't seen the demo, could you come up here and take a look and just confirm that, like, there's nothing funny going on? Like, it's just oil.
When the teacher asks like a magician.
Nothing funny.
Somebody
Yeah, okay, he agrees, nothing funny. So I'm just gonna put this one in. We're gonna say the magic words, and ta-da, it's become much larger. And the kids are like, ooh, ah, this has been hidden in here all along. And then I do it again, they say the magic words, and I talk about, and then I let them come up and look, and when you dip this in, it's just a larger stirring rod. You can actually see it disappear. It's just that it has the same index of refraction. So then we talk about index of refraction and how light is bending and how this is just a fun coincidence that vegetable oil and Pyrex have the same index of refraction. But you can hide things however you want, wherever you want. I like doing the 2 different size things because it intimidates the kids.
Yeah.
Okay. This is probably my favorite one. We're gonna move over to mechanics. So both of those are like 9th grade level. Honestly, it's not in C mechanics, so I don't bring those up in C mechanics. This is my torque stick. I put this together, I don't know. I built it pre-COVID. It's really easy. PVC pipe, drill holes, little joint, glue. And what I do is I tell the kids this is like a kilogram and like a 50-gram thing on a hanger, and I tell them, like, look, it's not that heavy, right? Not that heavy. You make them pick it up, it's not heavy. And I can hook it into my torque stick, and I can hold it really easily because I'm very strong. And then I usually yell, do you even lift, for a while. And there's always some kid that's like, y'all lift, y'all lift. So has anyone not seen this demo?
I'm not seeing.
Who doesn't? You seem like you lift. Come on over. You need to lift, bro. So this is what you're gonna do. You're gonna just like hold it horizontally with your hands right here, one hand here. Dude, it's a kilogram. Okay, let's try this again. It's just a kilogram. It's just a kilogram. So, you ready? Okay, just hold. You lift, right? Okay, come on. So take a seat. That was terrible. Who's stronger? Do I have anyone who hasn't seen this demo who's stronger than him? Adam, come on up.
I am not stronger than.
No, you're gonna be fine.
I am stronger.
He's so much stronger. So then the kids are like, no, it's unfair. And you talk about, torque, basically, and say, what am I changing? I have marks along the way, so I can put it at a mid-distance and talk about how as I change the radial distance from the pivot, the torque changes. And we draw the equation on the board and talk about the relationship. I use this for 9th and for APC, but it's like a fun gimmick. And if you guys want to try it later, it's actually quite dramatic between here, and I do let one kid try both. You guys have seen me do the close one, but like I can't do this. It's just not gonna happen. So it's a lot, which is very cool. So I'll put this back on the cart. My next, and that, like, the amount of PVC and glue you need for that is very little. This theme here is PVC. Here's some PVC and some gaff tape. This is my most finicky one. You actually have to practice with this in the back room a bit. I use this with my Honors 9 and with APC. So I've marked out, it's my free fall stick, I've marked out tape at even intervals, and the even intervals are about to my count of 1. Oops, see, it's finicky. Ready? 1, 1, 1, 1. So it falls to my own count of 1. So I tell the students it's going to fall to my count of 1. What's going to happen when I catch it and do 1, 2? Where am I going to catch? Where am I going to catch it at 1, 2? And 9th graders are like, right here. And 12th graders are like, at 4 because it's t-squared. Like, the 12th graders aren't super fooled. 9th graders, you can get like a solid 5 minutes writing the kinematics equations, talking about how T and D are related, and it really hits to that there's a, squared relationship between time and distance fallen. And this will take you like 4 minutes to put together. It will take you also probably like 20 to practice. Because it's just like fitting. I can't tell you how many times I've been like 1, 2 and grab it here. And the kids are like, I told you, and you're like, oh. So finally, the last one. This is just a bunch of washers. This one's in free fall too. Again, $5 or less if you have a lab attached to your classroom. Okay, so I'm gonna have to climb on the table for this, which I actually do a lot because it's my room. But sorry to pass the track. Okay. There we go. So I've taken, sorry, that probably messes up the camera. Which way am I dropping these? I've tied them so that when you drop them, and for some reason, this works really well with AP and really badly with my lowest level in 9th grade. They can't, but if you listen with your eyes closed, when I drop them, you get constant intervals between the sounds. So ready? So I think that's cool. Physics teachers think it's cool. AP students think it's cool. I have had no luck in 9 regular at this, but sometimes 9 honors, I'll get kids that are like, oh, that's cool. Yeah.
If you do 2 of them, one that's evenly spaced and one that's spaced with the distance squared,
Probably
they
be a
can
better
hear
demo.
the difference,
Yeah.
so then they understand the importance of it. And if you drop it on a pie pan, it makes a louder noise.
Ooh, that's a great, yeah.
And if you,
I've done this for years where I make the students put the student on the washers on the string, and the ones who aren't thinking space them evenly, and the ones who are thinking space them correctly.
do it with a lab quest and a microphone, and you'll get a graph of the sound
Great.
each time.
So yeah,
And
lots
you
of
can see the
extensions.
equals at the time.
Okay, so those are my 5 for $5, but if you want to build things for more than $5, which I have in this room, I know I've like already dragged a bunch of you to be like, check out my speaker. The speaker's awesome. I refuse to say that the speaker's anything but super cool. If you want to build bigger, more exciting things, you may have noticed that this classroom is attached to a machine shop, which is awesome. I'm very fortunate. This summer, there's a workshop here run by me and some of the other people to build, not these, you can build these on your own, you don't need me, to build bigger, cooler physics demos. I'm thinking definitely Rubens tubes. The torque stick's fun. We'll build the torque stick. The torque stick's cute. And if you want to lead a demo build, which I feel like the people, you're here because you want to share things. If you're like, I have something that I can build that's super cool and I could use a machine shop to do it, and money, because this is grant funded, so I have a few $1,000s to buy your equipment and your lunch, let me know. It's July 23rd and 24th, which is a Tuesday and Wednesday, so you can still be at the shore over the weekend. Come back Tuesday, Wednesday. It's just 10 to 2 to leave time for stuff to dry overnight. You will get to pick what you build. You will get to pick if you lead a build. I have spots for like 8 to 10 people, and it is free, and you get fed, and you get all the materials back to the classroom. So I've left some of these back there. They have the QR code to register, and emails also going out. It's not these things, but hopefully you'll join me this summer here to build something cool.
Paper plate.
I'm also not going to, hi, I'm BJ Enzweiler. I teach 11th grade physics at Science Leadership Academy, a poorly named high school. It's just a normal magnet school in Philadelphia. But I'm going to show off some things that you probably have seen before. Wires and light bulbs and switches. Ooh. But the thing is that there's a little bit of a process that I think is more interesting than just here's some wires and light bulbs. So could I get some help passing out papers to anybody? Cool. And I only got 4 kits because I only had 2 bags. So I'm going to spread these things out. And so I think people can kind of work together on these things to try and make something happen here.
You could make a group.
Yeah. Here, and I think we have enough on this side. We can kind of cluster some people in here. I'm going to say, looks like there's more centralization here. All right. And there's a group in the back.
Teamwork, everybody work together.
All right.
Make groups.
The people in the back got this kit. All right. So you're looking at this sheet. No, no.
I'll pick it up.
Oh, I'll grab it.
No. Thank you. Appreciate it. So on this sheet is a simple set of challenges. We know that the past couple of decades we've been pushing away from the kitchen recipe style labs, and we're trying to push students to try and do things on their own and figure things out on their own. This is the first lesson for me, is this set of challenges in my circuits unit. The reason it's the first set of challenges is because I don't really tell them what the heck they're doing. I just say, you need to try and do this thing. It allows them to explore how a light bulb works. It allows them to explore the idea of series and parallel circuits without ever knowing what those vocabulary terms even are. We don't focus on those things at first because we want them to see that they can even happen in the first place. So you've got on the left column there the list of challenges. And challenge 0 is, I think, one of the most important here, simply for just like normal life outside of the classroom. How does a light bulb work? Well, so you have to take a naked battery, 2 wires, and one of those little lamps in there, and make it light. Don't put the bulb in the socket. Don't put the battery in the battery holder. Use 2 sets of hands and see if you can make it light. And we, of course, know in this room how that should work. Well, let's see. I've got some sensors in there, some other things, but go ahead and see how to make it work. And then also, as you're doing this, think about how students might be making mistakes with this. What would students be trying to do to make this light? Just a naked bulb, just a naked bulb, no holder, 2 wires, and a naked battery. That's the 0th challenge.
You could just use 1 wire.
You could, but
And that's the
again,
Harvard.
it's figuring out how to hold it. I think is 2 wires.
Harvard video. I showed the Harvard video too.
Yeah.
Just gonna shuffle it over.
2 sets of hands is going to be useful here usually.
Because that's what I got. I'm 2 wires. 1 wire. What do you do now? Then you can just put this right on top of the battery.
Like the idea of wires.
I don't have inside now.
Yeah, just email me.
Yes.
So yeah, you've made them light. How would students? What mistakes would the students be making through this? So spend another 30 seconds. Talk in your groups. What would the students be making as mistakes throughout this? Just this 0th challenge.
Yeah.
All right, what are some mistakes our students might make through this process? Like just in this 0th challenge, what do you think? What are some things you're going to try and do?
Sorry, I've been volunteering.
Sure.
Not realizing that there's an insulator between the 2 ends of the ball.
Yeah. What else?
Shorting out the battery.
Shorting out the battery. Yeah, they'll just connect the 2 ends of the wire to the battery and then not forget about the light bulb. I've seen that happen. What else? I've seen kids touch the top of the light bulb with a wire and the bottom of the light bulb with a wire. And I'm like, but you know it's made of glass, right? But nonetheless. Some other things that I will very commonly see is I'll see them try to touch. So they know that the 2 ends of the battery need to touch the wires, 2 different wires, and then they'll try to touch both the positives to the bottom of the bulb. Because they're completely disregarding the threading. They see the threading, but they think it has one purpose only, to screw that into the socket. But it has 2. It is also one of our terminals there. And so this leads into like recognition. Like one of the principles of like current electricity, you always have to have an in and an out. Positive, negative, live, neutral, whatever you want to call it. You always have to have 2, at least, depending upon your objects, right? And so them seeing that and recognizing that is going to help them throughout the rest of this whole unit, that there have to be 2 things. In the kits, you'll also find there are sockets and switches. I want you to take those out because I think the design of these sockets, while not exactly robust, they do break really easily because kids just screw things in too much and then the riveting tears apart. But I think the design really helps them understand how the connections still continue to need to work. Because on those sockets especially, there's just a hole where you threw the threading in and then it jams onto a plate at the bottom of that blue disc. And it makes it obvious to the students how the connection points need to work in a socket. Same thing is true in those switches that you see there. Is that the switches, it makes it obvious there's a gap between where the switch can connect and where the switch doesn't connect the wires together. I will see kids try to put alligator clips on the little paddle handle for the switches there. I encourage them against that, but that's fine. And so I think those visualizations make it easier for the students to understand when they're first getting into this stuff. The old kind of switch with like the lever switches that have, I don't know, look like you're gonna turn on Frankenstein. Yeah.
Nice switch.
Yeah, that's the words. Yeah, thank you. Those, I think these sliding little ones work a little bit better just in terms of the conceptualization because on the knife switch, I always have them connecting to the knife part itself and it bothers me for some reason. I want them to connect to the little screw terminals on it, but nonetheless. Last thing is also these holders. I also really like, not just because batteries clip into them, but because they also then button into each other. So they can easily get those batteries in a line. So if you take those battery holders there and you squeeze them into each other, they actually hold. And so you can get 3 and 4.5 and more volts out of it pretty quickly and pretty easily. You can also slide the batteries into parallel, but I haven't really used that all that much. But you can see that there are like these little flags that stick out of the battery holders. You can actually slide them into each other so you can get the batteries in parallel. Again, I don't use it for what I'm doing, but maybe you might. But this is a good introduction to circuit electricity. Last thing to point out is the following day, you'll see on the bottom, there's that image is what I'd call a warm-up, which will light and which will not. And the following day, I'm always pleased with how many students know the answer just after this thing, because it's important to recognize where the terminals need to be. I saw a question back
I
here.
was
Yeah.
gonna say, after you showed us how to light a light bulb, if you go on YouTube and you put in how to light a light bulb, someone did like an interview or something, a survey at MIT, and I always show that to my students because you have electrical engineers, mechanical engineers that graduated that can't do that.
Yeah.
So it's good to show the kids that because a lot of them they feel like they're stupid that they can't figure it out, and you show these graduates.
Yeah.
But it's really easy to find on YouTube. You just how to light a bulb and you'll get it.
And that also reminds me, another one of the great things about just having a simple kit like this is that the students that probably should have gone to vocational school love this stuff. And the fact that they're able to work with their hands and try and figure these things out, and it's not super mathy yet, is really something that helps pull them into the rest of the unit nonetheless. Yeah. Other questions, comments, concerns people might have? Yeah.
I'll say with that, like, I don't have a with my students where they get like a cardboard box and Christmas lights, and they're passing things, switches, and all these things in wiring a house.
Yeah.
Bring out walls parallel, they need a main breaker, 50% breaker, each room needs a switch, all that stuff. And it astonishes, like, my emotional support group and my quote-unquote lower-level academically group, that they do so well with it, and my AP students have they can draw the circuit, but they can't figure out how to build it. And it lets them know, those students that sometimes write off science, that there are careers for them in science where they can be successful and support their families.
Yeah.
Like, they write off things like being an electrician because that's science. And then they discover with a thing like this, they can do that. They can do it really well.
Exactly.
So this is great.
Yeah. I'll leave the kits at the tables. If people want to play around, you're more than welcome to. I just want them back before I leave. All right. And intact, all of them.
Okay, so everyone should have the handout. Basically, this is the equipment. This is the Pasco friction block. It's felt, it's that. This is a friction board. I found it in an elementary kit. I can't find that anymore, so I had to find a more expensive one. It came with other blocks on it. These are the Pasco mass sets from the carts. You can use 2 of these. This one happens to weigh what 2 of these weigh, so it makes it easier. So what I put together was a series of things to introduce friction. I do this after I've already taught Newton's laws, free body diagrams, and things along those lines. So basically the last page takes you through the series of demonstrations. So the first thing you do is you have them push a chair. And these are on wheels, so it's a little easier. But when you push a chair, what happens is they can feel that it's harder, especially if it's not on wheels. It's harder at first and then gets easier. So once it starts moving, it's easier, and you have them sketch the graph. Because one thing you do when they're figuring it out, if they sketch the graphs, they begin to get a sense of something bigger than something small. And it forces them to do that. And then you just have them sketch it and discuss it and ask for what they think and everyone's perception, and you get consensus of the class. It was harder at first, and then it got easier. Then you take the friction block, put it on the cardboard, and this is cardboard, sandpaper, rubber, and cork. You put the weight on top of it, or you have the class do it. You take your Pasco, your vernier force probe, you set it on 10 newtons, you hook it up. You might have to bend the hook on it so it actually fits onto the thing, because the hooks are a little too small to fit on the friction block, but you can just bend it with pliers. It works just fine. It doesn't damage it. You take it off the probe when you're doing it. And then you hook it up to your LabQuest or whatever data digitation device you have, and you pull it. When you pull it, you get a graph, and you pull it so it goes at constant speed. That looks like that. And they do it at their seat, and you ask them, why do they have this graph? What does it mean? And they say, oh, it was harder at first, and then it was going at constant speed. It was going along. But I can't pull evenly, or they make some excuse why it's jagged. And that's fine. And you go through that, you have them unpack it. And then you go ahead and then, sorry, let me just go to my demos. You take these magnets, or any magnet, these are the ones I store ordered for the doors to keep them unlocked, and then they change the locks, so there's a bunch of them sitting around in the main office. And you put them together, and you pull them apart. And when you pull them, you'll notice that they're jagged. They're hard at first, and then it's jagged, it's up and down. So if you guys want to try. Anyway, so again, you get the same event that you just had. You get harder at first, and then easier. So you get into what's going on. And then there's a question that I put in there, does friction change on the fact, this resistance to motion change on the fact that if you're moving or you're not moving? Is there a difference when you're moving and when you're not moving? And then you get into how that's happening. You can take a diversion there and say what's going on. At first, you can see that you can get into the idea of the spot welding of electrons. You can get into however you want to do that to get into that. Or you can just let them have the phenomena that friction is harder when it's static and easier when it's not. And then you say what else causes friction. So what else is going on? How else can I change friction? Now the state of motion changes friction. What else does? So then you have them pull it where you have the wide side. Notice that it's 2 felt blocks instead of 1. You put it on the cardboard. You put this on top, and you pull, and you record the numbers. And they basically get the same numbers they did when they had 1. The numbers are almost insignificant. Like it's the error of the device that they get the number. So surface area doesn't play a role in their model that they're developing. And then you go ahead and double the mass on top, and that changes it. So now all of a sudden they've got about double the friction. A little less, but they can see it's more. So now they can say that the weight down, and more importantly, the force up between the surfaces is affecting it. Then you go back to the lighter mass, and you put it on the sandpaper. And obviously this is going to be a lot more, especially the static condition, because you have more of that grabbing between the surfaces. And then you go to the rubber, and the graph is basically flat. There's almost no difference between felt and rubber, between the static and kinetic friction. And then you go to cork, and it's similar to cardboard, and you've gone through and you've seen that the surfaces matter, and that the normal force matters. So then you can say, well, what are the factors that affect friction? And then you can go through them and develop the idea that the normal force is part of it, because that's the support force, and that. And then you can get into an explanation of what's going on, of how friction's happening between the interaction of the surfaces. You go back to the magnets and say, why did the magnets do that? Because there's a series of attraction and repulsion. What's on the surface of every material? Electrons. What's happening? The electrons go to places where they can interact and they're stable, and you have some stability, and then you pull them across, and as the electron slides past the other electron, it pushes it away. So you have less resistance because the electrons are overlapping, and then it goes to a point where the electrons are not, and then away, and where it's not, and you get that same staggered effect you have with the magnets. They can now explain that with what's going on in friction and what's going on in their graph. So you can basically take them through a more robust model of friction, and you can do this in about 45 minutes. At least I do it in my 90-minute block. I go through about half the class with this, debrief them, talk about, now what else plays a role? What would happen if I did this on an angle? And then you can get into, well, normal force changes with an angle because of the cosine effect. So there's a cosine effect there, there'd be less normal force. And then you ask them why a ball sits on the ground and doesn't roll, but if you put it on a ramp, it does roll. And you can get into the idea that the amount of friction change, and therefore it's able to go down and without the center of mass, but you at least keep it in the model of friction in something they can think about. And it gets into the free body diagrams and all of that. So that's kind of what I do as an ILD. And so I guide them through it. They have the equipment in the back, and I kind of have them go through those demonstrations in that series. with the questions that I have at the end to try and make them think about what's going on, so then we can go into a more robust treatment of friction than just an equation and just an idea. They've actually seen it and developed it. So that's about it. So.
Thank you.
Craig?
Yeah.
Yeah, just a couple of comments, right? So, I mean, you can spend the whole semester.
Yeah.
And just a couple of things. One is that the transition from static to kinetic friction is an unsolved problem in physics.
Oh, I know.
So it's good to show kids
Right.
that even the bench tops and
Right.
bench top physics can yield some really, intriguing results.
Mm-hmm.
Secondly, in the kinetic phase, right, that stick-slip,
Right.
stick-slip dynamics,
Right.
spans incredible numbers of length scales,
Sure.
right, from molecular motors kind
Right.
of things to earthquakes that we just felt like last week.
Right.
So it's a fascinating topic.
Yeah. So again, it's a great way to get them starting at it. Especially it's a first-year course for juniors, and they get juniors and some seniors, so it gives them a chance to see where this fits in. It gives them a sense of how we can take the lab and build an equation, how they're experiencing the equation is just a statement of the concepts they developed. So it's not me just giving them an equation and saying, use it. They've actually developed it, they own it, they have a better sense of understanding of it. You can ask questions like if you give them a case of this, and you pull, which one's harder to pull? Because they've seen that surface area really doesn't play a role, they'll understand that that's not really what's causing the friction, and that gets over one of the misconceptions. You can even talk about, you can talk about a lot of different types of test questions and ways to go about it. After they've done this, they have a better understanding of concepts like that. So, but yeah, as I said, it's just, something I've been playing around with and thought I should. So.
I title my round friction is a drag.
Yeah.
Question over here.
Oh, sorry, yeah.
Not a question, Craig. So the screws that you were talking about, that they can bend when you're attaching your flow sensor to the card. So what I do is I actually attach a thread between the two hooks.
But then the tension confuses them. I've tried that too.
Oh, really?
Because they think the tension has something to do with it, so the string had something to do with it. I used to do it with hook scale, like spring scales and things like that, and then I would tie a string to it, and that added that because it wasn't going directly to the sensor, so they thought they were doing something else. It added to a misconception that it wasn't me moving the sensor causing this to happen. The string was doing it, so they felt the string had something to do with it. So I took that out because it added to a misconception.
Yeah, there's a lot of misconception around strings and how stretchy they are for students. And so
So I just took that out of experience of when they weren't able to figure things like that out. So, but,
I'll just note the term ILD stands for interactive lecture demonstration. No, it's fine. Just for the newcomers, it's developed, I think, at Maryland, the Physics Education Research Group there. It doesn't matter. If you search interactive lecture demonstration online, probably Maryland, add to that. You'll get lots of good guidance on pedagogically how to like.
It's Sokolov.
Yeah,
it's tough. It's Tufts, Oregon, and it's
thanks. Yeah. Good guidance on how to actually use a demo as part of an overall pedagogical thing.
Here it is, I'll leave it up front if anyone wants all of them. I think I have more over there.
Thank you.
I want to apologize coming up prematurely. I thought that was it. Sorry about that. Yeah, felt like a goof. All right, anyway, I wanted to first promote this book. Paul Hewitt is publishing his autobiography. It's called Just Another Old Man Talking, The Awesome Life of a Physics Teacher. It's not published yet, so I'm helping him review it, so it will come out. I don't know when. So he's in his 90s now. So
I think when we saw him a few years ago.
yeah, I had him come to Villanova that one year, remember?
Yeah, that was great.
To speak. Yeah, and with Ken Forth was there. All right, so this is kind of neat that Craig did this thing on friction. I'm Geoff Wetherhold, by the way. I taught at Parkland High School in Allentown for 35 years. I had a planned retirement in 2020, which was great. because it worked out that I didn't have to do much Zooming. And then I was called for college because one of their professors died, and they asked if I could take over his course. So that's where I've been now since 2020, part-time. So I just teach one course, and it's great because I teach physics for non-science majors, and I'm using Paul Hewitt's 13th edition. And what's great about that is because I also taught one of those courses at the high school level, but unfortunately it always became a dumping ground. So the kids who took it, you know, I was great with demonstrations and activities, but unfortunately it was like students who didn't want to be in school, and it was horrible. And so it was really bad. All the teachers who teach it, it's like that there. For some reason, it just ends up being, hey, if you can't handle this, just take this course, you know. So it's great at Muhlenberg College because the students there really want to get good grades and do well. So it's like a dream come true to have to be able to teach conceptual physics at the college level. So, but anyway, this demonstration here, nice segue that Craig did for friction. So if you have a disc and you're going to exert a force horizontally at the center of mass, you ask the students if they can figure out conceptually maybe which way friction should act. Okay, so you just ask them that, which way friction acts on the disc. Okay, it's going to roll without slipping, supposedly. Okay, and they think about it, and then I pull it, and we'll see if their answer is right. So like that. And then you ask them, well, which way is friction acting on the disc? So it's a Newton's third law question as well. Right? So it should be right this way on the disc, right? Because the card is moving to the right, you're right, and right, so friction has to act to the left. And then I did this for several years, and then I was thinking, wouldn't it be neat if you could measure the force of friction? You know, somehow measure that. You know, I had ideas like using a motion detector, you know, getting the mass of this, using Newton's second law, right, things like that. And if you do it theoretically, you come out, if you go through this, and I have the derivation here if you're interested, but you end up with the force of static friction is equal to 1/3 the force you apply horizontally. That's what it comes out to be. So what I figured out to do after a while is just simply weigh this, you know, with the spring scale, and then put it into free fall. So the weight of it is the analogous to the horizontal force, and wrap the string around. Let me just take off these horizontal. All right. Okay. All right, so you just attach this to the spring scale like this, drop it, and this does come out to be 1/3. And what I recommend you do is videotape it, and then you can show it in slow motion, but it works really well. So that's what I wanted to tell you. Cool. It's pretty neat. Oh, the other thing is you can use, like if you use a hoop, an annular cylinder, but more like a hoop, it's pretty neat because you ask the kids, you know, the students, which way will the cart move? You know, so they have to think about friction and all that. It turns out it doesn't move at all. Right? So the force of static friction comes out to be 0 if you have the string wrapped around the perimeter of the hoop, like this. And I do that too. So if you pull it that way, and this is like a hoop, it's ideal, right? But it works pretty well with like a real thin-walled annular cylinder. You actually get a force. I'm sorry, you apply a force at the top, but the force of static friction comes out to be 0. Right, so when you pull it, like the cart stays stationary. Pretty neat. Yeah, perpendicular. Yeah. And then you can also like apply a force at the top. Right, you can do that. You know, ask the students which way the cart will move. Right, and then from that they can figure out which way the friction acts on it. So if you look, I think it moves. Let me try it again.
Is this for an introductory college level physics? Yes or no?
APC when I did it at the high school level, and at college, I teach science or physics for non-science majors, so I don't do this.
Okay, yeah, I was going to say.
Yeah. I mean, I might do this demonstration just when I teach Newton's third law,
Yeah.
just for interest,
Yeah.
but I don't go through the derivation. But at the C level was fine,
Yeah, yeah.
at the high school level, when I taught that. Let me just try this one more time. So, okay, I just want to see if I can get this going. Yeah, and if it did move a little bit backwards. It did.
No physics demo is perfect.
Oh, it does. Let me see. Did you see it move or not? Yeah.
Mm-hmm.
Move back. All right. So that means the force of friction is forward on it. All right, so I do have the derivation. I have 20 copies, so I'm a little bit more than that here. So take one that maybe if you teach at the same school or something, just take one. If you're interested in the derivation of that. Okay, that's it.
Cool. Thank you.
Yes.
Anthony, are you?
Sure, I'm here, yeah.
Yeah. I guess you're on.
Excellent, thanks. Anyone need a demo bag? I got demo bags for everyone. I got 10 demos in 45 minutes. I'll compress that into 10.
I'll take it.
Anyone else need a demo bag? I love demos, and everything in this bag was free. Free. The purple handouts. I teach at Princeton Day School, in a private school in New Jersey. I teach in a planetarium, actually, so I double up with astronomy. So I've been doing this about 35 years. I love what I do, and I love getting free stuff and giving it to everyone. So here's the purple handout of the demos I have, and there's some additional stuff in the bags. There's also websites on here, so you can find all this, some of this stuff online. I'll take these in order, and then I will go through a few of the other things in the pouch. Okay, first one's a two-way mirror. Everyone get this out of the pouch. I got these for free, but you can buy samples online. So everyone has it. Again, if you're missing something, let me know. But I think I did all this. These have been on my ping pong table since December 26th. So yeah, these are used for interrogation rooms. I gave you one of each. I like the acrylic ones better. You can cut them and drill them. And I put the percentages on there. So if you put it on your desk, folks, it looks like a regular mirror. But if you hold it up to the ceiling, it looks like, or some light, it looks like a regular piece of glass. So and of course you can shine a laser through here. It's sort of like a beam splitter. But if you put it between you and a partner with equal lighting on the same side, it's called Everyone Is You and Me. If you two had a child together, half and half DNA. Free. So I love these, and again, you can get a class set. Again, the website's there. So again, I prefer the acrylic much better. Next is the MacIver kaleidoscope, and that goes with this handout here. And so I made one for each of you. I'm like, this isn't going to work, and it really did work. So we build these, just get glass slides from biology, 3 of them, and then some electrical tape, and so it basically behaves like this. If you put a dark background on this, that's how this works. And so we make these in class. I do optics demos at the very end after Memorial Day. So it's actually quite interesting. And you can put your camera in here, your phone camera, and all that jazz. So again, these are just regular glass slides. You put black tape on the other side, it becomes a mirror. And that really turns me on mentally. I love this stuff. Optics, and I did sound demos last year. To me, those are the 2 top topics in physics. Really, of all sciences, I love sound and optics. Really. So there's your glass kaleidoscope. Next is the can oscilloscope. Has anyone ever made one of these? Herb Gottlieb did. All it is a can, balloon, and a laser mirror. I have plenty of those if you want them. Just email me. And then a little laser. Can we get the lights off or no?
Try.
Yeah.
The license group have their own.
And so, yeah, that's good. And so I just talk like this, and it really is one of the best demos involving sound and light And of course, I'm in a planetarium, so it's all pitch black and everything like that. So you're getting different wave properties here. Of course, if I sing notes, and I'm really good at singing, I love to sing.
Let's hear that boy.
This will turn on even the most jaded senior at this time of the year. So. Love this.
And then they're all going to want to do it.
Then they all want to do it, yeah. 100% participation on this demo. So you can also put the mirror on a speaker and play music, but it doesn't work as well. This clearly works the best.
What if you whistle?
Yeah, whistle.
No, but thank you for asking. No. Again, Herb Gottlieb, retired physics teacher, showed me this. I'm like, I gotta make these. So I think we made it by AAPT. Yeah, right. Again, very simple to make. Essentially free, except for the laser pen.
Anthony, do you have instructions how to make these?
I don't. You're there. Here it is.
Figure it out.
I'm gonna take a look.
Yeah, sorry. I don't have instructions. No.
I think the most curious part is how you kept that laser pretty stable on that thing.
It's a little
It's a spoon?
yeah, a little spoon from ice cream, and some kind of, I don't remember.
Steel bracket.
Yeah, it's a metal bracket. Yeah. Yeah. We used a fork. Just take a fork. You're good to go.
Bend it a little bit.
Yeah, bendable fork. Yeah.
Just go to some type of read or something.
Yeah.
Dollar Tree or something. Get a fork. It'll be cheap enough to bend it.
Where did you say you got the mirror?
That's not mine.
You can. Any mirror will work. I just have a bunch of front surface mirrors. This is a front surface laser mirror, which I
Could you
forgot.
use like a sequin?
Yeah, you could. Yeah, you could. You could just break a thin mirror. Sorry, I forgot to bring the front surface mirrors. I forgot that. But I do have some. A regular mirror would work too. You might get a little doubling effect, but it's really no big deal. So.
It's probably even a piece of mylar.
Yeah, Mylar would work. Yeah. Yeah, right. So I just love this thing. That's that. Oh, the submerged bulb. This was at this California, one of the California physics teachers group posted this online, and I have the handout for you. If you submerge a bulb underwater, this is just a regular incandescent bulb. It's a total internal reflection demonstration, and that kind of expands the bulb.
That's great.
You probably haven't seen that one before, now have you? So kind of an interesting phenomenon. And of course, the handout explains all the about the water glass interface. So again, I saw this online as a poster, and I'm like, I got to do this. And it's very easy to make. And again, you can search for that article. I printed it out for you.
How do you light the bulb? Take two battery and 2 wires.
Yeah, I have not plugged it in yet. That's a good point. Yeah.
But it has to be
Does it work with a
incandescent.
plastic
I think the
LED?
glass
bulb?
I don't know. I've only done an incandescent. The frostings, you got a
Where
frosting
would
on
you
it.
find one
That's what I said, it
nowadays?
doesn't work with a plastic LED.
Incidentally, you can light up the bulb in that configuration.
Yeah, you can light it up,
You
sure.
can do it as a heat
Yeah.
thermal demonstration
Yeah.
too.
Yeah.
Because it will work like that,
Yeah.
as long as, glass is intact.
If you put the bulb like that in a microwave oven and hit play, the bulb will
But
light
you
up.
have to submerge it before you light it.
Yeah, right. So just put the
Otherwise,
bulb in a
it's
microwave oven, just submerge it like that, and it will glow. It will glow. You can put things in microwave ovens that are metal, but you got to have a beaker of water.
It would be sketchy if I visited my parents, drove across the border to Mexico, bought a bunch of incandescent bulbs and drove back.
No. No.
I got.
Well, where are you gonna find incandescents in the United States right now?
I need my basement.
I got tons. I got tons. I want them for life. I got tons of them.
Oh, what, these board bulbs?
That's what I was
Yeah,
about to
come
say.
on.
I don't hoard things at home, only in my classroom.
Okay, everybody. Okay, fine.
Just so everyone knows, you should have a turntable and a bulb closet going.
Everyone, take out this pouch. We have the. Do we have the lights here?
You want them back on?
Yeah. Everyone has a little piece of film in this pouch. I went to a workshop 10 years ago at Rutgers where they deconstructed a laptop screen. And in a laptop, you have a piece of prism foil. So here's a laptop screen. I had a Toshiba which had 2 of them in it, and you all got a piece of it. So when you take this thing apart, there's a prism foil in there that has special optical properties. Who knew? And here it is. So I'm looking for old laptops. They're very hard to find. So everyone has a little piece of it, yes? Everyone has a piece of laptop screen. So take it out, and you can just put it up against and flip it. And there's a second handout about they did a lab with the kids, so that's where this comes from. So it has unusual optical properties, which can be examined only under a microscope. And so again, each of you gets a piece, and it does interesting things. We did a whole workshop on this, and so I've had this foil now for many years. So thank you all for being here, so I can give it away. I don't do this one in my classroom. It's a little complicated, but it's got 90 degree. It's cut 90 degrees, so it does total internal reflection one way, so we can backlight the screen. So sorry, you only have a little piece, but again, they sort of go through the entire optics of it. I was fascinated by this, and again, the second handout is the lab, which you would give your students. Of course, each student would have to have a little piece of this. So again, if you have an old laptop screen with an LCD, that should be, again, free. Okay, next backside. Okay, diffractive wafer optics. So everyone look in your pouch for this. This is from Tessera. They gave these away years ago, and now you're the last group to get these. I had hundreds of these. So, and then they stopped doing them.
You shine lasers through them and get different patterns.
Yeah, you shine lasers through them, yeah. Or close your eye and look at a point source of light. Can I get those lights off?
Yes.
You could look at my light, I guess, or you might get a rainbow effect. Maybe. You have to have it in the proper orientation. It even has a lens. It has a lens in here, and I put a little copy of what you can see there. Well, here's what I'll do this. I'll just you can keep this in your wallet and take it to all your physics parties you go to. That's what I tell my students. So.
Every party is a physics party when you break.
Yeah, and so you get the Tessera. There you go. This was called wafer optics. I don't know if they still do it. Not sure. There's the lens. There's the keyboard. I like the keyboard. Of course, if you look at it, you have to reverse it. Like you're loading film in a slide projector. So it's kind of cool.
That's the Japanese text.
Yeah, it is kind of interesting. I had hundreds of these. I only have a few more left. So one more group was going to get these. So.
Micro something, I think.
Micro optics. Okay, next one's the concealed currency. I can't. If you shine a UV light at the currency, it's hard to do. I need to be pitch black here. So, but if you shine a UV light, are you aware of that? The security stuff.
We didn't get that in our kit.
No. So, what I can show is the new polymer Canadian dollars. All the new polymer Canadian dollars. You can get these on eBay at cost, $190 for the whole set. And so it has a little diffraction in the little maple leaf. You need a laser for this, or just look at it. And so my wife doesn't know I do this. That's all right. So there's like a 50. It's 50. There you go. Kind of cool. Or you can just look at it like so. So yeah. So. I have bills from all around the world. I got about 95 countries. I'm trying to get every single country on earth. So when people go on spring break, they always bring me back money. I love money. We're almost done here. What's next? Everyone has, these are optically pure glass marbles. Not your everyday marble. I got hundreds of these and I've been waiting to give them away. The students don't care. Now you get these. You're the only group that ever will get these. So these are optically pure glass marbles. Put it in the clothespin, and then you can do demos with it, like so. Again, these are not regular marbles. This is optically pure glass. of all different sizes. Everyone got a random, you know. Some of you have a clear. Some of you have a frosted one. Some have frosted ones. You get a single frosted, but again, so that's that. I got these from AAPT. It's not on the list. This makes a line. This gives you a line like so, kind of a line. Like so I got these from AAPT. The acrylic, I finally got these cut the other day. I've had these for years, you know. So this is like a little page magnifier. Then you make words that are symmetric in letters, like cookbook recipe. Cookbook doesn't appear to flip, but recipe does. Make them different colors. You can really mess with the students. Again, everything in here was free. And then, okay, the final demo is the Pulfrich effect. Anyone aware of the Pulfrich effect? Everyone take out your goggles. I got these from Brian Jones at the summer meeting. If you don't have these, you can just pop out sunglasses. I get these for free. I go skiing and they give these out at the happy hours and stuff, or just by dollar store and just pop them out. So this is a stereo illusion demo. Here it is. So Brian Jones did this one, and I'm like, oh, I have to do this one. So everyone put your goggles on. It doesn't matter which side. I don't know if this is going to work. Can we get this higher maybe? How can I get this pendulum a little higher? Can I prop this up somehow?
Yeah, sure.
A crate or something?
Yeah, I have a small,
So the pendulum's going to go in a plane, but you're going to see it go in a circle.
crate.
Because the time delay between when it hits your eye, I'm like, you got to be kidding me. So if you make it go in a plane, we'll just make it go in a plane, and now it's going to appear to go in an oval. And then flip the glasses around, and it goes the other way. There's a time delay between how the light reaches your eye. It's a little delayed, just a tad delayed. Again, it's going in a plane. I'll do it again. I'll go in a plane. You have to be perpendicular. So if you're over on the edge here, you want to go in the middle. You all look great. You all look great. I'm going to get a picture of all of you. This is called a camera.
What?
Oh, wow.
And now switch it, and it'll appear to go the other way.
Don't they take advantage of this for like 3D glasses?
Yeah, maybe.
Some forms.
But again, you have to watch it because you have to get it really. I'll do it again. I'll try to make it as good.
Like, Anthony, can you run back and forth?
I didn't hear that. It is kind of like, you got to be kidding me. And again, so Brian Jones gave all these out, and then I wrote him. He gave me hundreds of these goggles, and I've been waiting to give them away for 15 years. So thank you for being here. And again, it really is going to a plane a bit, and then it's weird. It's a stroboscopic effect. Again, I have a class set of these, and I give them to the kids, and they give them back to me. So.
I'm totally doing this at the end of the year. Just be like,
As I said last year, remember, I'll leave you with this.
Class period. Right there.
Physics rules. Always remember that.
just watch this.
I think I went through everything in the pouch. Yeah. There's other random. There's random. These are overhead projector lenses, free. That and I've been wanting to give these away. Like there's a DVD. There's just random filters and everything else. Mini lenses. My dentist saved dental mirrors for years. Everyone gets dental mirrors.
If you put that string closer to it, and then you do that, it literally looks like the string is going around.
It's amazing.
Going around the pole.
It really is.
And it flips directly if you switch. And a regular color filter over one eye will keep
Money at the
do
item.
the same thing.
This is optics part 1 for me.
I need one lens.
I have so many optics demos, but
Yeah.
any questions on anything?
Thank you
What's
so
with the
much.
piece of wire?
Yes, she does.
So how many of you have seen these before? These are called Galton boards. What I want to do is talk a little bit about this and some different things that you can do with them. So if you're not familiar with these, they're sort of like a Plinko board. So the idea is that it has a bunch of little pins here, and then as these balls come down from the top, they hit these little pins, And at every pin, it can either bounce to the left or to the right with 50% probability of each. And then they end up landing in these little bins at the bottom here. So technically, this forms a binomial distribution, so it's Pascal's triangle with increasing values of n. But this approximates a normal distribution for a sufficiently large number of trials. So a couple of examples here. So it does help to visualize what I might call the bell curve. What I wanted to do is come up with some relations to experimental physics. It might be a little bit more valuable to us. What we can think of is when you conduct a measurement, right, that's just like one of these balls hitting, and maybe there's a little bit of error, right? Maybe you're a little bit one way, maybe you're a little bit the other way. If I were to conduct an experiment, and an experiment is just a series of measurements, then each one of them is like bouncing off one of these pegs. And there's a little bit of error. I measure a length, I measure a time, I measure a speed, whatever. Maybe it's a little high, maybe it's a little low. You can think of it as sort of like bouncing off of one of those pegs. So if you do a bunch of measurements, or if you do a series of measurements that contribute toward one value, what you're going to get at the end is your ball, which lands in one of these, which depends on how each of these pegs came out. So your final value is going to be normally distributed, like that. So just think about sort of each measurement that you make is sort of a plus or a minus. So now if a bunch of people do measurements, or you conduct a bunch of experiments, you're going to get a normal distribution like that. Now your measurement, this one here, there's one ball that's a slightly different color than all the others. So if we have 1,000 students, 1,000 monkeys typing on 1,000 typewriters, right, your measurement is one of these, and it's going to fall someplace in here. Now, maybe you end up a little bit above, maybe you end up a little bit below. That doesn't necessarily mean that you made a bad measurement. Right? It could, right? If you mess something up along the way, then you're going to get a value that's way off. But just because your value is off, even potentially by 2 sigma or even 3 sigma, doesn't mean that it's a bad measurement. It's just that when you did your measurement, the errors conspired to add one way or the other. So what do? You conduct many different measurements, and you take the ensemble average of them, and that's going to be the mean. And we expect that the mean is a better estimator than any of the individual values. And that leads to talking a little bit about standard deviations. So what's one standard deviation? That's the 68% confidence interval. So about 2/3 of your measurements will come within one standard deviation of the mean, but 1/3 will be outside of that. 2 standard deviations is 96%. So in a class of 25, which is about what we have here, probably one of you is going to get a 2 sigma outlier. And that doesn't mean there's anything wrong, right? That's just the way that statistics work. So you can talk a little bit about that. You can also talk about statistical versus systematic errors. So everything here we're assuming is random, which means that if you do more and more measurements, you can beat the error down, right? It's 1 over square root of n, which is slow, but it works. But what if we had a systematic error? And a simple way to model that is, let's see, make use of something here. What if I did that? What do we see now? You still get a normal distribution, but it deviates from the mean. And no matter how many measurements you take, it's always going to be deviating from the mean. Right? And in a lot of ways, that's the worst type of error. Right? It's where you're very, very wrong, but you're very, very sure that you're right. There lies the road to hell. So you can think about statistical versus systematic errors. A little kind of a bonus thought here. If you do any propagation of errors, right, there's always that weird quadratic formula where you have to add the 2. So where does that come from? And you can think about correlation of errors. Right? If I have 2 errors that are perfectly correlated, right, that's like bouncing off one peg and going to the right, bouncing off the next peg and going to the right, well then I want to add the errors. Or it could be that the errors are perfectly anti-correlated. Right? One goes to the right, one goes to the left. In that case, I would subtract them. Well, if they're not correlated and they're not anti-correlated, well, what's halfway between? How do we add 2 numbers like that? Pythagoras. Now, you can go a little more complicated from there. You can think about correlation coefficients and so on. But yeah, if you think about them as sort of orthogonal, that kind of naturally leads you to that quadratic formula. So if you want to get one of these, I actually looked on Amazon last night. These are sold out right now. Hopefully they'll come back. There are bigger ones that are maybe more suitable for classroom. I think they're 12 inches. There's a couple other brands that are out there. The smaller ones are maybe like $30. The big ones are more like $100. You can download the app. There's one for the iPhone, and that's good so you can simulate it. There are also some computer-based simulations. Let me see if I can open that up here. Let's run that at high speed, and you can get a histogram. So there's a lot of fun you can do with that, simulating normal distributions.
Does it allow you to do the analogous thing of tilting it to?
You can. You can adjust the p-value here.
Oh, okay.
Right, so the p is the probability that you go one way versus the other. So I could make that like 0.2.
Got it. Okay.
So I think that means a 0.8 probability of going to the left and a 0.2 probability of going to the right. Let's run that at high speed. All right, so that's going to give you a distribution like that. So kind of fun to think about. Maybe I'll pass this around and play with it.
So what do you teach and how does this fit into what you actually do in the class?
I'm still thinking about how to use it. It might be useful in the lab. This is something I've sort of thought of in the last couple of weeks.
Yeah, totally fair.
It could be useful in the lab, just talking about errors.
Yeah, I think just when you bring up error in experiments, like the reason why we do multiple trials all the time is because of this. We don't have time to do as many balls there are in that thing, but we do multiple trials to try and find a mean and do all that. Like, it's simple as that.
Yeah, some students have the idea, oh, error, that's a bad thing.
Yeah.
Well, and it is, but it's a thing that you have to deal with.
Also, I've seen this done as from scientific publications, especially in certain areas where you get 25 people who are doing a paper, and there's going to be a good chance that one's going to get a very significant result off the mean, and so they will say, oh, you know, we have worthwhile results, and those are the ones that often get published because they have the worthwhile results, and they may not actually be worthwhile. They're just a statistical error. I mean, of course, that's hopefully not the way people would initially go, but that's being used as an application.
Yeah, it works in a few ways, right? So if you have a very large outlier, you may reject it. Oh, something was bad. So then you end up with a normal distribution that's been cut off. Right? You get outliers that should be included in the average end up getting thrown out. And then sometimes you have outliers that, wow, that's interesting, let's publish it.
Right,
so they can get overrepresented as well. That's why you always have, every couple of years, chocolate is bad for you, now it's good for you, and now bacon is good for you, bacon's bad for you, because you just get this positive noise. You have one study that is an outlier, and that's the one that gets all the attention.
Yeah, I had a question, like, let's say you had like 1,000 things that you had to check, like you're a quality assurance engineer. Like how would you figure out, and I don't know, like how many you should actually inspect of those 1,000? My dad used to do that, but I never really understood exactly how he did it. Does anyone know how they do that? Is that related to this a bit?
Well, I don't have these.
Like you wouldn't have all day to inspect 1,000, so you might inspect 10 of them or 20 of them.
It's an interesting question. Essentially, it's when you test another batch, the results didn't change. Some successive numbers of times in a row, but every company will make that decision for themselves based on, are we getting better quality versus spending more person hours finding if we have high quality? So I don't have an answer for you, but that's how it's done in practice.
Yeah, he used to inspect for DuPont, they train wheels that were going on the chemical cars. So he had to inspect the wheels to make sure they were tapered correctly.
I'm going to write this company. I'll try to get everyone a free one next year. I'll get back to you.
Pink card? Look, I just get the $100 bills, so we'll take that. Yeah, it's interesting. This thing hasn't changed at all while we were talking. It's still running.
Oh yeah.
Really free trade.
So I have one of these on my desk, and I love it. I just hate the fact that it's named after this horrible human being. Galton was the father of eugenics, in case you don't know. Terrible racist.
I did not remember that, but now I do.
So if you want to call it a Carlo board, you're welcome.
What don't we know about you, Jeremy?
I haven't invented
That's just they are, right?
Proto, I mean, yeah.
Hi.
You speak to this
Let's say if we want to turn the one on the screen.
Your warlock status hasn't.
So this controls the front lights. This doesn't really control. So these two are the front lights. This is the one on. This is the witchcraft that. And sometimes if you just go to the circuit breaker.
Oh.
Yeah, maintenance loves that. Do you want me to? So just hit HDMI.
Okay, so before I do my thing, I just want to say I use modeling instruction in my classroom. If any of you are interested in modeling instruction, we have a physics first workshop and also a chemistry workshop the last 2 weeks in June at St. Joseph's Prep. So if that is something that interests you at all, please talk to me later on and I can point you toward the sign-up site for the workshop. Okay, so this is what I'm going to talk about today is this piece of software. If you want to know where this piece of software came from, it came from two places. One, I've been using the FET charges and fields simulation for years in teaching electricity and magnetism, and always felt that it was lacking certain things that I would like to have. It had lots of stuff that I liked, but then there was more stuff that I wanted, and then the summer of 2020, locked in my house during COVID came, and you know, what are you going to do? So this is my response to charges and the FET charges and fields. It has, for example, grid. So when the grid is on, when you place charges, they're locked to the grid. So it allows students to precisely position things. If that's not important, they can turn the grid off. It has a bunch of different things. And so the real reason I started this was for this one, because everybody wants a capacitor. And if you want a capacitor, you sure as heck want to see the field lines and the equipotentials. And then you want to see what happens if you move the capacitor plates. It doesn't draw the equipotentials live, but I turn down the integration, and so you can see the field lines adjust as you go back and forth. Of course, it's a lie. There's no way that in real time you could actually do metal plates because the complication is iterative and too complicated. So these are uniform charged plates. So it's an approximation of a capacitor. So you can see that the surfaces are not equipotentials, and we're not violating any physics because they're not metal plates. And you know, if you want to spend more time exploring a dipole, there's the dipole, and like the capacitor plates, you can move the dipole. There's the half dipole charge and plate. Right, if you go back, let's go back to the dipole. And I will just turn off the equipotentials because, right, you can make both charges positive, you can make both charges negative, and you can change the strength of the right-hand charge to show asymmetry. And then if you want, if none of the stuff that's sort of pre-programmed is to your liking, there's the sandbox, where now you can put anything you want in the sandbox. Also, charges and fields has this other thing. They don't do field lines, but they do this sort of grid of compass needles, and I really kind of like that. So if you like the compass needle display, that is also here, if I can find the button, right? So that's sort of the charges and fields approach. There's just too much on the screen right now to really see what's going on. So one thing that it does, suppose you want to make a charge stronger, you can take a second charge and you can put it on top of the first one, and if you get it close enough, the program will say, oh, that's what you want to do. You want to make a charge that's 2x, right? And if you put as many charges as you have the patience for. Because it's JavaScript, which has absolutely incredible resources. So, whoops, I didn't quite get it right. You have to get it close enough, and then it says, oh, that's what you want. So now that's a charge of 3 nanocoulombs instead of 1 nanocoulomb. So, it's there's a bunch of other stuff on this website, and so if you go here and you're interested in other stuff, I've got other stuff there. Yes?
Will the test charges actually move across the screen?
Oh, the test charges, of course the test charges will do their thing, right? Of course I've erased the thing that I made. So let's use the dipole. Yes, the whole test charges is, they'll show you the force, and then when you let go,
Cool.
okay, it'll do all of that. There are, just like the FET thing, there's field sensors. You can put the field sensors anywhere you want, they'll stay. If you want to see the values, you can do that. And if you want to draw your own equipotentials, you can grab this, and then it will press the button, it will draw an equipotential, and if values are on, it will show you the value of that equipotential. If you do the, let's put the voltmeter away. If you do these equipotentials, it doesn't put values for those, but you can always figure out what it is. You can use the voltmeter if you can't tell. Yes?
Before, when you showed the charge going across,
Yeah.
were those equal time intervals to see the acceleration in principle?
Yeah, they're equal time intervals, yes. So, it's integrating, and when the integrated time gets to some value, I draw a thing on the screen. So yes, they're definitely, you can definitely tell velocity. And I mean, you can do all kinds of crazy things with the test charges, because But I didn't get it quite right, because if you position it right, it just goes back and forth on the exact same trajectory until the clock runs out on it. You have another question? Go ahead.
Yeah, just in principle, if you had just one charge and a point charge, could you simulate even though it's electrical, universe squared, would you get an ellipse?
No, because I don't have any way to give you an initial velocity for the test charges. Right, you can only release them from rest.
Okay.
So, but an orbits program is on my list of things I'd like to do. But there's a good one on the FET's website, so why should I duplicate the effort other than that I need a hobby?
Yeah, there was a program called EM Field by Physics Academic Software years ago, around the early 2000s but obviously it's been orphaned from Windows updates. It's now part of WebAssign. I think they bought the software. But what they used to do is they used to do magnetism with it as well. And they used to do, when you have your field direction, they would do a heat map in terms of color going down the rainbow. So, and then they could, as you click on things, it would actually just show, you could get the color, you could do a line instead of field direction, you could do a line of the color of the heat map. So it's just something you might want to think about adding, or at least look at the original program, which is called EM Field.
Okay. I mean, one of the reasons this exists is there are lots of orphaned programs out there.
Right.
Right? Mm-hmm. So this is, runs on, it's a web program, so it should have a longer lifetime before it gets orphaned. But the thing that actually started me down this, I'll leave this open and just open another tab. Oh no, this is not where I wanted to go. I wanted to go, does anybody remember electric field hockey? Right? That was an old PC program, I guess it was on that too, and it went away, right? And so I really wanted it. So this was the first program that I wrote for electric field stuff. And it's, as best as I could make, a real sort of copy of the original program. And then it turns out that Ruth Chabet at the same time was, while I was doing this, she was making a new version of her electric field hockey program that runs on something called GlowScript. So we sort of both came out with these at the same time. So, but if you remember that old electric field hockey program, for obvious reasons I couldn't name it electric field hockey, so it's electric ice hockey instead. But it's as close as I could make to the original
It has the
program.
hidden charges and everything else?
What's that?
It has the hidden charges on level 9?
There's no hidden charges. There's no hidden charges.
Yours is the frictionless example.
What's that?
Yours is the frictionless example.
Right, yes.
Ice.
Okay, well that's all I have.
Geoff, I missed what you said about, do you have any negative?
Raise your arm, hope that somebody will find you.
Okay.
Call an Uber, yeah.
All right, we got a chance, some friends of ours had a condo in Florida. I don't go south. I much prefer hills and cool weather. So we almost always go north. So these friends of ours had a condo in Florida. They said, why don't you come down? You got a free room. And I thought, I guess I should see the place. And I realized that we're going to do our normal trip at the end of the summer to Maine. So I was going to be in Florida and Maine, and I thought, wouldn't it be cool to take a look at the North Star from all these places? Okay. So long ago and far away, I taught an astronomy course, and we did an astrolabe where we sighted the North Star. Okay. And you take a straw and you look at the North Star and you have a plumb line on it. And of course, it's all wrong, because if you're at the equator and looking straight north, the plumb line's pointing in here and it's reading 90 degrees. And if you're at the North Pole looking straight up, it's reading 0 degrees. So you actually need the complement of the reading on this protractor, which is quick, easy, you can do it. Okay. So I thought I could do that. Or I could look at the way it's been done. So here, to prove I was in Florida, the Wawa has palm trees. Okay? So this really was Florida. Okay. So we've got GPS units that solve all of our problems with almost no curiosity. So we're located in, we've got 3-dimensional location plus direction, and it's on this. Okay, this isn't even a fancy device. Okay, so you know which way I'm pointing. We've got latitude, longitude, and elevation. We've got 3 dimensions. Okay, it's all there. It's a complete act of faith. All right, and it would be nice if we could take care of this some other way. Part of my thought, I'm retired, so it doesn't matter at all, but I strongly felt that the way to teach physics was to sneak it into the students' lives. Like, you haven't taught it if they're not taking it home and thinking about it. And so last year I was doing a thing where you're taking your water bottle if you're hiking in the hills and closing it off and using it as a barometer / air density. Like, you know, here, you can do this with the stuff you're living with, okay? So one of the issues we've got with all this GPS crap is that we are at the end of the golden age of GPS. I don't know, are you thinking? We're worried about the Russians putting nukes in space, not because they're going to drop them on us, but because they're going to blow up satellites, because they know damn well that we've become slaves to external guidance. If you've been listening, Israel right now is very concerned about external attacks and is talking about scrambling GPS. A good robotics class right now could whip up a guided missile. And I think that we are in an era when terrorist things happen, they're going to scramble GPS, and folks who can't drive without it are going to be up Schitt's Creek. And you know, I think we need to think about that. Okay,
you know, we had this little era when people hadn't figured out what they could undo with GPS, but we're now there. So inertial guidance would be a nice thing. Well, we can do that. Because every physics tool that I learned with in the 60s is on your phone with an app that you might pay $5 for, but odds on it's free. So there's a clinometer. So you can get the clinometer here, and you can sight the North Star along your phone, and it's got a hold on it. And why didn't I do that? Because I needed the phone to take pictures of the other stuff that I was doing. Okay? So I went to the store and got my general relativity equivalence principle device, okay, which is a digital level, all right? And so it can't tell the difference between gravity and acceleration, and that's just peachy, okay, because all I got to do is look at one, all right? So you can look down this, and it turns out most of these digital levels have a magnetic strip with a little crease on the bottom so you can put them on steel things. And if you turn it over, they also are clever. The numbers turn over. So this is a little hard to haul around. Okay, it's big enough to see. We can turn it off. But these days, you can get little ones. So this is $30 at Home Depot or wherever, okay? It's got a hold button on it. The magnet lets you, you know, and you can use tape and a straw, but if you have as much crap in your basement as I do, you've got little springs, okay? So you can take a little spring, put it on the magnet, and now you've got a tube, okay, that you can sight through. And it turned out that the metal of the spring was reflective, so I wrapped it in tape, okay? And so now I've got a device that I can sight, and after I find the North Star, I can hit the button, freeze it, and get my reading, okay? And this is entirely self-contained. My friends all want me to get an Apple Watch. I still have this big clunky thing on my wrist. My hobby is getting as far away from the world as possible and seeing if I can take care of myself. And Apple Watches stop working if I succeed. So I've got, this is just a pressure barometer in here, which is, you know, self-contained. It's also got a magnetic compass in here. So even if I lose track, and the other thing, I don't know if you've gotten your ass deep in the woods, the worse the conditions get, the less likely your GPS is to work. Overcast or a leaf canopy make it really hard to find satellites. Okay, so, you know, this is a fair weather friend for many, many reasons. So in any case, I took this gadget down. If you take a look at how it was done in the past, and I brought this in, and once again, okay, excuse me for being evangelistic, you guys get to talk about this every day. I have to wait 6 months for these damn meetings, and they give me 10 minutes. And I would have told you how to find the North Star if I had 11 minutes, but I don't, okay? So you can find the North Star on your own. This equipment, you know, and I'll make this statement from the ground up. Old school buildings, you know, like these buildings that were built in the 20s, 30s, and 40s were the best buildings in the community. They were these gorgeous things, masonry or stone construction, pillars. It said people cared about education. These were high school buildings. They weren't prefab buildings. This hardware says that these guys gave a damn about what they were doing. When you look at this, you said it's got vernier gauge dials on it, it's got all kinds of stuff, and you're going to believe what this tells you. I don't know whether you're going to believe what this tells you. This is like a magic little box, okay? Now, I kind of know what's going on in here, and I believe it. But in terms, I think one of the problems we have with credibility in science today is we don't have people looking at the stuff that's used to get this information. You know, there was a lot of work put into getting this information. But this is big and heavy, hard to move around. That's light, but not very accurate. During World War II, they miniaturized it a bit, and there's a second doodad back there. This was a gadget that was used in airplanes during World War II to figure out where they were. Because while the planes externally look about the same, they had way less technology. The crazy thing about this is actually a pretty good gadget, and I'm going to use it in a minute. To put this on an airplane where you give a damn about what stuff weighs, they had a wooden case that would cost over $100 to build today and weighs about 2 pounds. I mean, you wouldn't dare waste 2 pounds on an airplane on the case for something anymore. But both of those gadgets have this case. This was used, one of the many obsessions I have is my father worked on the Martin B-26 Marauder bomber, and of course the obsession extends to having a manufacturing plate on my Yeti cup. Okay? You probably haven't gone that far with your madness yet. But the way they would figure out where they were, there was a hatch on the top of the fuselage, and the navigator stuck his head up here with this gadget to figure out where they were. That would have been these guys in here. And here's the guy who does that, okay? Hard to imagine a world where this was the way you took care of things while you were being shot at 600 or 700 miles from home, okay? So anyway, here's the gadget. I use this gadget at home, okay? Home, of course, is the Philadelphia area. This is telling me that the angle at which I could see the North Star read 50 degrees, but we all know this, that's the complement of the number I want, so the number is 40. So I took out my doodad and I used it, and ta-da, it says that it was 40 degrees, okay, in Springfield, Delaware County. And if I get out my magic GPS unit and have it tell me I'm in Springfield, Delaware County, almost 40 degrees, okay, not bad for an eyeball measurement, okay? So that was the initial plan. And so here we go. This is when we've decided to stop just across the South Carolina border. We're at a Best Western, and they're wondering what the hell I'm doing out here, okay? And the North Star is now down to 34 degrees. Of course, we want to do a cross-reference, so we pull out the magic box and say, what the hell's going on? We're in Latta, South Carolina. It's 3420. We got 3430, okay, which is pretty good for an eyeball measurement, okay? Here we're a little further south. We're in Jensen Beach, Florida. We're getting 28 degrees, and they tell me it's 27 and change, okay, which isn't too terrible. Notice the lighting is not conducive to finding stars. So then we get a little further south. We had a family, the plan was to go to Key West. We had a family issue, and they said, no, your adventure's only starting. You have to get home in a day. So we drove straight home, and I didn't get to Key West, but we'll report next year. So we get here, and that's 26 degrees. Now, it is kind of a pain to sight this, whether you're using your iPhone. So what I discovered makes sense, because if you're in developed areas, there are buildings, there are trees, and there's more lights than you want. You can walk all over the place, because remember, the North Star is infinitely far away. There's no parallax, right? So you can find an object that you can use as a pointer and get to where the North Star is right there. So luckily, where we were, the North Star was monstrous, okay? And I could place it directly above the point on that roof. Because looking through this little hole, it's pretty hard to find a really, because the North Star is not a very bright star. Okay, you know, people who haven't done astronomy think, oh yeah, it's the big, but no, it isn't. It's just the one that's in the right place, and it's pretty dinky. So if you find your pointer, then your North Star is there, and you get pretty good numbers. Okay. Whoa, too far. All right, so we're in Weston, Florida. We're getting 26 degrees, okay, and they're telling me it's 26 and 7 minutes, so we're pretty good. Okay, so how does that all work out? And I think units conversion, we hide so much understanding behind this mishmash of units. And it is, from like energy is, you know, the poster child for that mess. Okay, but it turns out that a second of arc is about 100 feet. So if you've got your iPhone with your latitude and longitude, walking 100 feet is going to change it by a second. Okay. Nautical miles, if you haven't jumped into that, a nautical mile is 1.1 normal miles, and like, why do they do such thing? Well, there's 70 Earth miles in a degree, which doesn't match up with circular measure. So if you make your miles a little bit bigger, you have a couple of fewer, and suddenly there's 60 nautical miles in a degree. Each nautical mile is a minute. Okay. So from Springfield at 40, we got to Weston, Florida at 26, which gave us 14 degrees times 70 miles, means that we went 980 miles south. And if we look at the odometer on the car, we're at 1244, and I did not have time to get the map of North America and do the Pythagorean theorem for this annoying non-north-south line that I-95 travels on, okay, which is much more challenged temporally than spatially because mostly it's gridlock. So my space-time continuum, that it may be time that's adding to that distance. In Florida, there is a recognition of the fact that navigation needs several backup systems. There are lighthouses all over the place for when your astronomical sighting isn't going to get your ship home. And you know, again, we're kind of getting ourselves hung out in space. Let's go back home again. How much time do I have? When are you going to shut me up?
A little over, but take a couple minutes.
Okay, because this is so cool. The 40 degrees, which is where Philadelphia is, you know, we kind of take for granted. Okay, but if we go back to 1632, Charles I granted Lord Baltimore the ground up to the 40th latitude line. Okay, so that was all of Maryland. All right, and then we sneak up a little bit, and Charles II, okay, the British royalties had their head up their asses for a long, long time. Okay, so Charles II gives William Penn some of the same ground. Now, in theory, he says it's 40 degrees, and William Penn says, great, and then they get over here and they say, oh my God, the capital of my place is in Maryland. Okay, because, so they now get into this big fight over whose land is where, okay? And so in 1763-64, they get two credible British surveyors, two guys named Mason and Dixon, okay? And Mason and Dixon come over and they're going to plot out this thing and settle this dispute. And it's decided they got to take some land away from Maryland. So Philadelphia, and if you can believe this, the line was defined as 15 miles south of the southmost house in the city of Philadelphia. It was a house on South Street, clever, okay? And there's a marking there in Philadelphia now, okay? So we get down to 39 and change, all right? And here's Mason and Dixon, and look at what they're using. Now, what they're using is an instrument that they get from the Astronomer Royal in England, okay? A guy named Maskelyne, okay? And he gets them set up, all right? For those of you who remember Davis Sobel's longitude book, and if you don't remember it, maybe you didn't read it, and you should, okay? Maskelyne's the villain. Maskelyne's the guy who keeps Harrison from getting the reward for making the clock that lets you find longitude. Okay, and that's what I thought about Maskelyne. He's a bad, bad guy. Okay, so they make their measurement, they get the Mason-Dixon line, okay? This craziness, the arc, of course, is the 12-mile arc around Newcastle, okay? And that was all predefined, but they can't sort this out. This wedge, they were fighting about this. They settled this in when? 1921. They hadn't decided who owned that land until 1921, okay? Because they got tangent lines, they got north-south lines, they got arc lines, and they couldn't. So don't be too rough on your students when they have trouble with geometry, okay? I mean, like this is, so 3943 is going to be the line. And if we come down here, all of a sudden we're in Boulder, Colorado. Okay, this is the Flatirons. You know, if you're obsessed with climbing, okay, first, second, third Flatiron. Right up here is, they painted over it big monstrous letters CU for Colorado University. They go up there and paint that every football season, and the National Park Service goes up and paints over it with paint that's the color of those rocks. So these are 1,200-foot slabs that you can climb. If you get up to the top of the slab, you have this view. Here's UC Boulder, okay, and you're looking down here, and this is Baseline Road. And what is Baseline Road? It's a road on the 40th parallel, okay? So it's 40 degrees north latitude. Oh, no, I want to go this way. And if you look straight out there, you can see there's Baseline Road, and City Hall is right there. Okay, you can see it right there. Okay, so 40 degrees is of some consequence, but let's keep going here. All right, so you've got to go to Wikipedia and read about the Mason-Dixon line. All right, because there's so much going on. So here these guys are doing all this stuff. Okay, and so down here, in reality, they didn't get a line. It was a polygonal chain, a series of adjoining line segments between 3943.15 and 3943.23. Maskelyne's incensed. It's like, oh, my equipment didn't work. This should be better than this. Okay? So he says, well, you know what? Maybe the Allegheny Mountains screwed up your plumb line. And he goes and talks to a guy named Cavendish to think about whether there's an issue here, okay? And so Cavendish talks about all of this stuff. They get that sorted out. They decide that that may be a problem. They go up to Scotland with a plumb line and do this experiment where they actually ascertain how much gravity this mountain, this is a mountain in Scotland that's conical, so they can figure out its volume. They use that to get the density of the Earth. They get 4.5, it's actually 5.5, but pretty good calculation. And then a few years later, Cavendish shows up with the Cavendish experiment because he realizes that so Maskelyne ends up not being all that bad a guy, okay? And Davis-Sobel doesn't give you the full picture, but you know that basically the Mason-Dixon line triggers the Cavendish experiment, which is, you know, I was kind of impressed. And the Brits get used to doing this junk and bring pendulums to the Himalaya when they first start exploring, because they want to figure out the gravity of the Himalaya, and they discover way, way off, you know, once again, they thought they were just verifying things. There's less gravity than they expect in the Himalaya, which of course today we know to be the fact that the stuff on top is the light stuff, okay? And that these mountains, granite is less dense than basalt, floats to the top, and there's a root of granite under the Himalaya that's not as dense as the basalt that's under the oceans. But all of that is coming from there. So, and thank you for the extra time.
Bill, what do they navigate with in the southern hemisphere? Can't use the North Star.
There's the Southern Cross, but mostly, yeah, they don't have a single star, which is why nobody lives there. and why, you know, very few continents have chosen to be there.
Bill, it seems to be you're like this close to mentioning Aristosthenes and getting the radius of the Earth.
But I only had 10 minutes.
Well,
If you guys want to stay all day, we can do the whole thing. Yeah, we can walk from Syene to Alexandria. And
Homework did you bring another shirt and you can go to the car and
yeah.
have an alter ego name put
Right.
down?
Bill, I could listen to you all day. And I don't say that to too many people. You're awesome.
Thank you.
A major failing of myself facilitating a meeting is not having Bill laugh. That was silly. Deepika.
Yep.
Thank you.
That's fine.
Always makes them happy. All right, so hi everybody.
Hi.
I'm Mary. Safety first. So I was thinking about things that are simple. I've had this luxury of being at Penn for a little while, and a lot of times when we want a thing, we buy a thing. And it's mysterious to the professors that a lot of times we will try to make the thing. And they're like, why would you do that when you could just order it? But not every classroom, Ryan and I come from classroom teaching, and not every classroom has the money available to just do classroom, or to just buy a thing that they want to find. So what do I have here, and what am I going to demonstrate here? I have a simple nail attached to some neodymium magnets that are clearly keeping this string in tension. I have a blowtorch and I'm warming the nail, and what I'm hoping to show is the Curie effect. So the Curie effect is the temperature at which a ferromagnetic material stops exhibiting ferromagnetic properties. And the reason why this is a valuable demo in your intro E&M classroom is because we can't see the domains. We tell children and college students alike that the reason why things are magnetic is because all the electrons are aligned. They all act like tiny little magnets, and we ask them to believe us. And sometimes we make electromagnets and they believe us, but we don't really show them that we can disrupt those aligned domains. And so what I'm doing here is I'm heating up this nail because I don't want to destroy my magnets, right? Because they don't come back as easily. And that is going to disrupt the domains. And we can see I didn't touch the nail, it just lost its magnetic properties. And I can cool it down, which is always exciting to the students. It might still be a little bit warm, but I can put it back up there and it sticks again, right? So Curie effect, it gets at the things that they can't see happening inside of materials that can be ferromagnetic. But then later, what do you want to take home for your students? I love your $5 demos because that's what this is going to be. What could a student take home and be excited about and be the smartest person at the dinner table? They could make a motor at home. And so right here I have a simple AA battery, a nail that I've attached tape to for demo reasons, and another neodymium magnet, which these days, those used to be really expensive, but these days kids can buy them at the store, or they can order them online for relatively cheap, or it might be within your budget to order a classroom set for them. If you send students home with neodymium magnets, you have to remind them that if a small child swallows more than one, they will die, right? So remind them that
one's okay?
One, you'll poop out. Two, they're gonna find each other, and then they're gonna rupture your intestinal wall. So I did not learn that the hard way. All of my children are alive and well. But so I've taken this, this battery, the nail, and the magnet underneath. The magnet's aligned all the domains in the nail. It now attaches to the metal on the battery. And now I've taken a wire and I've connected it from the top of the battery. I'm going to connect it to the bottom of the magnet, but when I go to the bottom of the magnet, nothing happens. Well, basically nothing happens. But if I go to the side of the magnet, and now the kids can wow their family members with how smart they are, and they've just become electrical engineers, right? And they can do this at home, and it fascinates them. I'm not going to lie, you can watch it for hours. How do I know you can watch it for hours? Because I was doing this at my dad's house last night, and I thought we killed the battery. And my dad was very excited about this. So, so this is a great demo that students can take home, that they can build themselves with materials that they can find at home. Interesting things worth playing with. If you attach a light bulb or an LED to this circuit, suddenly we have enough of a load on this motor that it doesn't turn anymore. You've just connected the circuit, which brings up a whole other fascinating discussion about when we put loads on things. And so those are just my little electricity and magnetism is a tough thing for kids to get a handle on, to visualize at that nitty-gritty level. The Curie effect shows you that we can align and misalign those domains. And this is just a great little thing that students can be doing at home and be excited about your class even when you're not there. That's all I have. Go for it.
You've ever been to the Exploratorium in San Francisco?
Yes, yes,
So-
but like 25 years ago.
So they had this strip of iron within a range of a magnet, so it would be pulled toward the magnet, but you could run a current through it and it would get hot and go through the Curie temperature and fall back down and cool down and be sucked back to the magnet. I think I spent about an hour pushing that button.
Yeah, exactly. And it gets, at so many different things that you get to talk about with this demo, and it never comes up. The Curie temperature never comes up in your classroom. You don't have to teach them the math about it. You don't have to teach them any of the other magnetic points. You can just show this to them and prove to them, yeah, we can align these domains, we can misalign them.
So Mayor, I guess if you hook a thermocouple up there, you can actually calculate the Curie temperature then, right? Or measure it.
Absolutely you could. Absolutely you could. It would take more instruments than what I have here and than what most of us have in a high school classroom, but it could be done.
And it's also interesting, nickel has a lower Curie temperature. You know, like you can play around with, other metals and.
But the flame makes it exciting. Fire! Oh, and I'm going to say one other thing before I hand it off to Ryan. I think there's video of this today, and if you get the opportunity, you should go back through every single word that Bill said, because every single sentence of what Bill said reveals something that you could spend an hour delving into and bringing back to your classroom. So, it's my public service announcement.
Thanks all. This has been really tremendous. I hesitated to sign myself up for a demo because the list was so long, but I'm just gonna go for it. I don't know where I first saw this demo, but it remains one of my favorites. And this is how I start an electricity unit. I don't know, we can figure out how much money goes into this, right? Find this in the trash can,
Trash.
We've seen this many times, trash. You can sacrifice a wool blanket. Static electricity. And what I do is, I've done this totally silently, where I just say we're going to observe and write down observations. And it's going to take us a long time to explain how this is happening. You charge up a PVC pipe, you can attract the can. You can attract the can. Okay. Why does that happen? Ideas? Go ahead.
Induced dipole moment.
What does that mean?
Attracting a positive charge in the can on one side and a negative charge on the other.
And whatever's closer is going to feel the force more and
What's going on? I did it on my right and it worked. Now, my 9th graders in a physics first class have no idea what any of you just said. So what I do is, I hand out a paper with this shape on it, and I say, spend the next 20 minutes, spend the next 5 minutes just writing down what you think's going on. And there's scaffolds for that. I have leading questions. Then I get them into groups of like 3 or 4, and they have to make decisions about how do I represent what I think's going on with this. And you invariably get some representation of the pipe, and they're going to make guesses. If they know what charge, heard that word, they're going to start making guesses. They're going to say, this thing's charged up now. It does the thing like my sock's on the floor and I touch the doorknob. That's from everyday life. And they know that there's a force pulling it, because typically you do this after mechanics, right? If it ends there, it ends there. So the real explanation is that this is negative. We do experiments to find out which one's which. And a good model would represent the positive staying put, but the negatives rushing away to the other side, exposing an imbalance of positive near the pipe. That's why it works both ways. You all said this already. So what I'm saying to you as teachers is, look at this demo, write down your best adult physics person explanation of what's going on. That's your electricity unit. Then we go through a series of, we do the Scotch tape, we do stuff with electroscopes, we do the field hockey, any number of activities, and we're constantly revisiting these drawings they made on posters that are up around the room. And we do like gallery walks, all the things that you hear at teacher talks. And they're revising this picture they draw iteratively over 2-3 weeks until they can have, and then they have like blurbs on this. And by the end,
I think that's my timer going off.
it is your timer going off.
I do have one more thing to add. I forgot to draw a diagram.
Yeah.
That can come up later.
Draw a diagram? What do you mean?
Like, a lot of people don't know why the thing spins.
Yeah.
And why where you connect the wire works on mine. You keep going.
Sorry. That's kind of it. Because the only other thing I could do is say, come sit in my classroom for these 3 weeks and see how we do it. Yeah.
Yeah, Ryan, I'm going to be retiring soon, but I typically teach E&M in July and August. And you know what happens?
Yeah, it doesn't work.
It
doesn't work.
It doesn't work. But I found online a little handheld Van de Graaff generator.
Yes.
I love it. It's called a Fun Fly stick.
Yep.
And actually, I was going to at the time demonstrate exactly what you did.
Yeah.
And I'll tell you what, it works great.
It works in all weather.
It works in all weather. Not underwater, but it works in all weather.
Jeffrey.
And then when you get into magnetism, what I do is I take a neodymium magnet
Yeah.
and you just have the students figure out how you can get the can to move with the neodymium magnet.
Great.
They discover they have that relative motion.
Yeah. But something, I feel like if I'm getting good at teaching, it's that I don't let myself stomp all over that first day of what do you think's going on here? Because that's your resource for addressing their ideas and shaping them and changing them over time. Yeah, this demo shouldn't be answered in 10 minutes. Thanks, Bob and Kathleen, for getting the food. Thanks, Alissa, for hosting. Thanks, Anthony, for all the free gadgets.
I'm already planning next year.
Bill's sighting equipment is out on the table. So it wasn't just, a PowerPoint show. It's here in the room. I think that concludes the festivities.
Thank you so much.